Hello students, welcome back to JCE Connect series of lectures. In previous class, we have seen the working proportions and design parameters of a Pelton wheel. In this particular session, I'll be taking one numerical problem, that to analysis problem on Pelton wheel. Let us take a problem, that is a Pelton wheel is receiving a water from a penstock with a gross head of 510 meter. Then one third of the gross head is lost in friction in the penstock. Then the rate of flow through the nozzle fitted at the end of the penstock is 2.2 meter cube per second. The angle of deflection of jet is 165 degree. Determine the first one, the power given by the water to the runner. Second, the hydraulic efficiency of the Pelton wheel. Take the coefficient of velocity as 1 and the speed ratio as 0.45. So this is the problem given. Here, the first we need to write the given datas. The datas given here are gross head of the Pelton wheel is given, that is 510 meter. Head lost in friction, that is HF is one third of the gross head, that is to be lost in friction, that is 170 meter. Then the net head available at the inlet of the turbine is, that is a gross head minus the loss 340 meter. And the discharge is also given 2.2 meter cube per second. Then the angle of deflection 165 degree, means after hitting the jet into the blade, then it will deflect by an angle of 165 degree. Then the angle pi will be, that is the vane angle at inlet will be pi equal to 180 minus 165, that is 15 degree. Then the coefficient of velocity as 1, that is given. Then the speed ratio is Ku is 0.45. Okay, so these are the given datas. So what is been given here, see in this one, in this figure, the given the gross head of the water. Okay, the gross head of the water is been given, that is 510 meter. Then before supplying water into the penstock, the head available in reservoir was 510 meter. As the water starts flowing through the penstock, so there will be a loss because of the friction in the pipe. Because of the loss, you will get the friction loss, that is HF. So that is friction loss HF. Then the net head available at the inlet of the turbine, this one, the net head available will be Hg minus Hf. Then how much this HF to be taken, they are given in the problem. This HF, that is loss due to friction, will be one third of the gross head. Okay, I hope you understood this one. Then the angle after passing water to the blades, then the angle of deflection will be 165 degree. Okay, with this, next, so this is the velocity triangle you have to draw first. This is the cross section of the blade. The blade will be like this, and this is the splitter. This will be the splitter, and the water is coming and hitting this splitter, and the inlet velocity triangle will be straight line. And you have to mark all the components of the velocity, that is a velocity of the vane u1, this is the relative velocity of the jet with respect to the bucket, and the jet velocity is equal to the whirl velocity. And at inlet there will not be any flow velocity, and the bucket will be moving in this direction. So this represents the inlet velocity triangle. Once the jet strikes, the water will be gliding over the surface of the bucket like this, then it exits. Then the angle of deflection can be represented as 165 degree, it is given in. So total angle is 180. 180 minus 165 gives you pi. That is the angle at outlet of the vane. Vane angle at outlet will be pi. That is 15 degree. Then you have to draw this outlet velocity triangle. This represents the relative velocity. Then draw the jet velocity absolute, that is absolute velocity. Then the beta will be acute. Then mark this u2, that is velocity of vane at outlet. Then this is a vw2, whirl velocity at outlet. Then this is a vf2. So mark everything at outlet tip of the bucket. This triangle represent the outlet velocity triangle. So with this outlet velocity, with this velocity triangle, now we need to calculate the force exerting by the jet on the bucket. So the power given by the water to the runner, so we need to calculate this one. So to calculate the power given by the water to the runner, first we need to calculate what is the velocity of the jet. The velocity of jet is given as v1 equal to cv root of 2gh. So this is the actual velocity of the jet which is acting on the bucket, that is cv root of 2gh, where cv is the coefficient of velocity that is given 1. Then the velocity we get 81.67 meter per second. Then after this, the velocity of wheel, that is u equal to ku into root of 2gh, where ku is 0.45. that is also mentioned in the problem. We have to take the speed ratio, that is 0.45. then the velocity of the wheel will be this much, 36.75 meter per second. Substitute all the values, that is velocity of, that is a g and h, all you substitute. The h is the net head available at the inlet of the turbine. Then finally we get 36.75 meter per second. Then referring to the velocity triangle, you have to calculate the relative velocity vr1. vr1 will, because we know this u, then vr1 will be v1 minus u1. Then you have to calculate that vr1. So referring to the figure, that vr1 will be v1 minus u1. So we get 44.92 meter per second, because u1 equal to u2 equal to u. Also you have to calculate vw1. So vw1 is equal to v1, 81.67 meter per second. Then also from the outlet velocity triangle, we have vr2 equal to vr1. From the outlet velocity triangle, this vr2 is equal to vr1. Since they are not mentioned any losses in the passage of the bucket, so we have to assume vr1 is equal to vr2. Means we are assuming this passage, that is the blade passage, is very smooth. There is no any frictional losses. So vr1 is equal to vr2. Therefore vr1 is equal to vr2 is equal to 44.92 meter per second. Then finally vw2 to be calculated. Again referring to the velocity triangle at outlet, vw2 will be, that is this one. This is vr2 cos pi. This whole, this is vr2 cos pi. That is the component of vr2. This one horizontal component of vr2. Then vr2 minus u2 gives you vw2. That is vr2 cos pi. vr2 cos pi minus u2 gives you vw2. This is vw2. That is velocity of whirl at outlet will be 6.64 meter per second. Then the work done by the jet on the run per second. The work done per second will be what? So rho q. This formula we know, rho q into bracket vw1 plus vw2 into u. This is the force exerting by the jet. Force into velocity of the bucket will gives you work done per second. You have to remember this formula. Okay, actually this is q equal to a into v, then this is mass per second, then vw1 plus vw2 into u. Substitute the values of rho, that is 1000, then q is 2.2 given, then vw1 calculated, vw2 also calculated. Why plus? Because the beta is acute angle at outlet velocity triangle, then velocity of the bucket, then finally we get this much. Then the power given by water to the runner, so just to divide it by 1000, we get 7139.863 kilowatt. Okay, that is Newton meter will be the joule. Joule per second gives you, joule per second is watt, that is kilowatt. Then after this, what hydraulic efficiency also you have to calculate. To calculate hydraulic efficiency, so hydraulic efficiency you have to calculate hydraulic efficiency. Hydraulic efficiency of the Pelton wheel, that is, this is the formula to be used. Hydraulic efficiency, this one, 2 times of VW1 plus VW2 into U divided by V1 square. Okay, then you will be getting this much is efficiency. I hope you understood this one. This is the work done per second, that is then the velocity of jet, or else hydraulic efficiency you may calculate. Hydraulic efficiency, that is work done per second divided by kinetic energy per second. Calculate separately work done per second, kinetic energy per second. When you substitute these two values, you will get this equation in derivation. You know this formula, then substitute all the values here, then you will be getting hydraulic efficiency. Okay, so remember this formula, 2 times of VW1 plus VW2 into U divided by V1 square. So why V1 square? Because kinetic energy per second will be half mv square, that is we get kinetic energy per unit weight of water. Then when you substitute that one, we get V1 square by 2, then the 2 goes in the numerator, then we get this equation, then we get 97.3%. Okay, we'll continue next class, one more problem. Thank you.